So, Dr. Shukla, thank you for the kind introduction. Now, I would like to proceed with my talk. Today, my talk is on the topic of quantum energy teleportation. Quantum energy teleportation is a form of quantum information transfer. So, what is quantum information transfer? Quantum information transfer is the transmission of quantum information from one location to another without losing the information and preserving the quality of the information. However, the term quantum transfer is basically used for quantum state teleportation, or as one generally calls it, quantum teleportation, where transmission of any physical quantity is not involved. Teleporting physical quantities to remote location is a remaining key challenge for quantum information science and technology till date. As we know, energy is a physical quantity. Theoretically, the protocol for the teleportation of energy from one quantum system to another is already discussed 15 years back, with energy transmission faster than the time evolution rate of the system. However, the role of the quantum energy teleportation in physics is largely unexplored as the theory has not received much attention for a long time since it was proposed. But very recently, the first experimental demonstration of quantum energy teleportation on real quantum hardware has been observed, according to new research that also cites observation of energy, negative energy. So the present proposal assumes to extract the concept of entanglement using tripartite entangled systems for quantum energy teleportation. Before proceeding further, I would like to give a small intro on common terminologies used in quantum theory. So, causality. Causality states that any effect cannot occur without a cause that never happened in the past, or alternatively, any cause cannot have an effect outside its light cone. The other most used term is locality. Any object is influenced directly by its immediate surrounding or for a cause to have an effect at another point, something in the space between these points must mediate the action. That is, it is said that any event at a point cannot cause a result at another point in the time less than t is equal to d by c, where c is the speed of light and d is the distance between the events. But quantum theory defines it using entanglement. An entangled system is defined to be one whose quantum state cannot be expressed as a product of individual wave functions or its local constituents, but is instead represented as a superposition of the product states. Now, returning back to the point where we left, I would like to continue with quantum information transfer, which is our main topic. We have quantum information transfer, which has been achieved through various processes of quantum teleportation. Quantum teleportation was first proposed by Bennett and colleagues in 1993. It is not as per the image of quantum teleportation we have in science fiction. The actual image of quantum teleportation is given on the left-hand side of the screen. On the left-hand side of the screen, stated as quantum teleportation. So the PRL paper is given on the right-hand side of the screen, which shows the first teleportation using EPR pairs or entangled pairs. So a quantum teleportation is a protocol which involves two parties, usually Alice and Bob, that schemes allows Alice to send information about an unknown quantum state to Bob, who is then able to construct a copy of that state. To do so, the pair exchange classical information over quantum channel while sharing particles that are entangled quantum mechanically with each other. While this formulation of quantum teleportation does not provide a means of energy exchange. Quantum energy exchange. Now heading to the very much recent topic, or one can say that this topic is the topic of quantum energy transfer was actually established in 2008 by Porta, where he unveiled the theory explaining how energy could be teleported using the energy of the vacuum system. However, in quantum field theory, um, it is said that the vacuum is not devoid of energy, but contains virtual particles that continually bubble up and then vanish. Quantum energy teleportation has been studied theoretically for spin chains, ion traps, quantum Hall effect, and various other theoretical models. By teleportation of energy or energy transfer, we mean that Bob can receive the energy much faster than the energy can be transmitted from Alice to Bob in the natural time evolution of the system. So the protocol uses the ground state of many body dynamics. The ground state of many body dynamics, a many body system has a special property of entanglement. In many body system, measurement plays an important role. It can give rise to excited states, which in turn increase the energy expectation value. So here, local measurement of a subsystem can destroy the ground state entanglement at the same time, and the energy from the device making measurement is injected to the entire system. In quantum energy teleportation, the role of measurement is very important. So if a pair of systems entangled, so if we are transferring some energy to the first particle, say Alice, and then try to make a measurement of the first particle and think that we can get the entire information about the energy. So it is not possible because the information about the entangled system is stored in remote location other than A due to the entanglement that exists prior to the measurement. Quantum energy teleportation is the protocol that makes this possible by combining local and classical local observations and classical relations and conditional operations. The crucial property of quantum energy teleportation is that it can be realized entirely by the general nature of the ground state of the entangled quantum many-body systems and the universal fact of measurement. So, using the ground state entanglement, the phase diagram of many body systems are reproduced by quantum energy teleportation, where Alice and Bob coordinates are fixed and teleported. Energy to Bob's local system reproduces the phase structure. Those findings suggest that global structures such as symmetry, topology, and long correlation of many body systems can be detected by simple local operations. One does not need to measure all qubit or states, which is advantageous for research in quantum physics using quantum computers. Recently, Kazuki Ikeda from Stony Brook University reported the realization and observation of quantum energy teleportation on real superconducting quantum hardware by using several IBM superconducting quantum computers. Now, I would like to start with the proposal that I made in this context. So we start with a set of tripartite entangled systems. This is the set of tripartite entangled system. Okay. So this is my system A, and this is my system B. These systems are then segregated. First, the two systems are, we are taking tripartite entangled system. So there is a property that the ground state of tripartite entangled system are highly entangled. So this property can be used for the quantum energy teleportation. Now, what we are doing, these two entangled systems are, we are entangling the two particles, the one particle from each system to the other particle of the other system. let's say this is particle A, B, and C, and this is particle A1, B1, and C1. So the particle C is entangled with B1. Now further, these systems are segregated from their surrounding at a minimum distance. Then a random particle is brought in the vicinity of system A. The energy of the entire system is then determined both with and without the foreign particle. So what actually happens, one-to-one connection is made between every particle in the system, and then it is perturbed. The outcome shows a notable change in the system's energy density value. So when we perform the measurement on the system, we assume to get the result in the favor of quantum energy teleportation. As I can explain it, for when we are introducing a foreign particle in the system A, then it will have an effect, or after the measurement, the energy which is injected from the measurement device to the system can be utilized, and after some unitary evolution, it can be regained from the system B. So for the measurement of the system, we use the compass state. We can use other states also, but here we are using compass state, which shows superposition of 4 Gaussian or coherent states. Okay. So the first term, these are the 4 Gaussian terms. The first term is the displacement in the P naught direction, minus P naught direction. Second term is the displacement in the plus P naught direction, whereas the remaining 2 terms is the displacement in the minus X naught and plus X naught direction. Here sigma is the squeezing parameter, X naught is the displaced parameter in position space, and P naught is the displaced parameter in the momentum space. So we perform this measurement using the compass state. What we calculate, we started with calculating our Wigner function for the system. The Wigner function is a mapping of density matrix to the phase space. The probe acts, the compass state acts as a probe here. So in order to check the properties of the compass state, we perform the Wigner distribution, where we got a chessboard type structure. And one can say, why is it useful? Because in quantum energy teleportation, Alice and Bob's coordinates are fixed, and the teleported energy to Bob's local system reproduces the phase space structure. So the compass state is a very sensitive state, which can sense even a small change in displacement in the space in the X direction or the P naught direction. So here for the measurement of the system, we can use compass state. This is the Wigner function, which is plotted corresponding to the state. And then next we have calculated the Fisher information corresponding to the system. So the Fisher information actually tells the amount of information that an observable carries about an unknown parameter. The equation of the Fisher information is given here. For the pure state, it is the variance of the expectation value of the observable. So here we have plotted the Fisher information corresponding to the compass state. The figure shows that with the increased value of the sigma, we have used the plot for sigma is equal to 3. The value of the Fisher information decreases as we increase the squeezing parameter. Okay, so overall, the work is under progress. So more technicalities of the work is not discussed here. So, okay, I think the talk is over. Thank you.
Thank you very much, Manali, for this interesting talk. So, is there any question by the participants?
Hello, ma'am.
Hello.
Yes.
I have the question how the information is transferred without decaying and any disturbance in quantum teleportation. Or is there any setup for this?
Okay, so yeah, actually, the teleportation of energy is actually a physical teleportation. So it is only performed in a local system. I mean, people have shown it for very like for a short distance. Till date, it has not been achieved for a very long distance. So for a short distance, there is something which we called as local operations. Let's say we are having any a system of two particles. So what happens when we give energy to the first particle? The energy of the system is increased, and then after performing the measurement on the first particle, the measurement injects the energy to the system, and then the unitary evolution is performed on the second particle, and then we extract the result. But I cannot say that the energy is extracted as much as we are giving in. The energy decays in rate. So it's not that we can get the complete energy of the system as much as we are giving.
Thank you, ma'am.
Is there any other question?
I have one question.
Yeah.
Thank you for your talk. I would like to understand how did you derive Fisher information expression?
How did I derive?
Yes, a Fisher information expression.
Fisher information expression. Okay, so the Fisher information, like, are you asking? Okay, look, the Fisher information is corresponding to the probe. Okay, can you see the slide?
Yes,
Yes.
I can.
Okay, so this is the compass state, corresponding to which I have calculated the Fisher information. Since the compass state acts as a probe to the system, so the remaining system after measurement is kept aside, and the probe acts as a lead. So once the measurement is done, we take the probe and then we measure the system, and then we measure, the properties of the probe. So the Fisher information is measured corresponding to this probe. The probe is the compass state, which is a pure state. It is not a mixed state. So the Fisher information corresponding to the pure state, as you can see from the expression, this is the expression of the Fisher information. The first term, delta square H 4 pi, this represents the Fisher information for the pure state. H is the observable, which can be, you can check what is H from our, okay, so this is the cat state. So the, this is the compass state. So when we perform any unitary evolution to the state, we can check the corresponding H. For example, here the variable is X, as you can see everywhere. X naught is a constant, P naught is a constant, sigma is a constant. Only the remaining variable is X. So we perform the expression of H is given by, for pure state, iota dou by dou of the parameter. So in our case, for the compass state, the parameter is X. So we can calculate H. H is iota dou by dou X. So corresponding to that, we can apply the, okay. So we can apply we can check the expectation value corresponding to the compass state. The Fisher information for this compass state is the expectation value of the momentum. So we have the expression bra psi h square cat psi into 4 times, where h is iota dou by dou x. Okay, so by this I have derived the equation, and here is the result in the plot. Is it clear now?
Thank you.
Okay.
Manali, the plot which you are showing,
Yeah.
so what is on y-axis and what is on x-axis?
Okay. Oh, sorry, I didn't wrote it. Okay. So on x-axis, we are having P naught. P naught is the initial momentum. And on the on the x-axis, we are having P naught, and on the y-axis, we are having the Fisher information. It says that as the Fisher, with the increase in the value of the P naught, Fisher information is increasing.
Okay, and in expression, where what is delta?
Okay,
Yeah,
delta square, delta is the variance.
variance of what?
Variance of h, where h is iota dou by dou x.
Okay. So,
Okay, you can say it as an expectation value or the variance of the momentum. Since the compass state is a pure state, okay, as you can see, the compass state is the pure state, and we have only one observable, or we have only one parameter, which is x. P naught, x naught, sigma, h cross, all others are constant. We have only one parameter, that is x. So if we define any unitary evolution, which is given by e to the power iota p x, iota hx. So here x is the observable, and the h, which is p. H here is the momentum.
yeah, okay.
Is
Okay,
it now
so
clear?
go back. Yeah, it is. So just go back to the slide where you were showing this Wigner function.
Okay, Wigner function. Yeah.
So the figure which you are showing here,
Yeah.
so what it physically means? Means you are measuring some.
Okay, so this actually means this is showing the interference pattern in x and p direction. So what does this means? That even if these small interference pattern has the phase space structure which even is less than the h cross by 2. So this can be, this is very much useful in quantum metrology for sensing. So what happens, the interference pattern can even sense the small displacement in the x naught and p naught direction. So for these interference patterns are used. So when we perform any measurement, we can see there is a displacement in the x naught or p naught fringes. One can, okay, so when we are seeing the middle part of the Wigner function, so the interference pattern is corresponds to the minima and maxima. So if we are performing any measurement, the minima and the maxima will shift by some amount. And once we can, and the shift can be detected through this interference pattern.
Okay, very good. So, is there any question? Any other question?
Yeah, I have one more question. Sorry. Could you please share the references which you used while preparation of your presentation?
Okay.
I can ask in the chat. So there is no.
Actually, the references that I have used for this I think I can mail you through the QIQT team.
Yes, thank you.
Okay, actually the quantum energy teleportation, this system is quite new, and one can say the actual realization, the experimental realization of the quantum energy teleportation has been achieved very recently in 2023 itself. So this is a new topic. So yeah, I can send you the references.
Thank you.
Okay.
Okay, thank you, Manali, for this talk. So the next talk will be